Today's topic is going to be role of hardware accelerators in packet processing. In this topic, we really want to focus on how the evolution of computing, particularly with respect to packet processing, the course that you are all involved in, the 7 layers of networking, looking up a MAC address or an IP address, and how forwarding the traffic takes place, and how that is swinging from one kind of model to another due to technology development, as well as the requirements of the network over and over, right? So that's the topic of what we want to talk about. Generally, as part of the Intel requirements, whenever we give any talks, we need to put up this legal disclaimer so that it's understood that I am presenting as myself, and any numbers, etc., that I may talk about, you cannot hold me in a court of law. Things like that. When you're a big company, you need to make such disclaimer. So in the agenda itself, we will talk about the CPU. Many of you would know some details that I'm going to talk about. You would have already heard about it, you would know about it, but I wanted to tell this story in one big swoop. So we'll start with CPUs, then we'll talk about accelerators and how we got there. And then if you are plugged into what is going on in the computing world today, it's not just CPUs and accelerators alone. There are so many different variations, right? So we are not going to get into all the variations, but at least wanted to mention that as to how different types of computing, whether it is communication or a data processing or website or running different loads on the cloud, so many different types of computing elements are needed in today's world, right? And so when you go into building a solution, you need to consider all the options that are in your toolkit. That could vary from CPU to accelerators to other processing units that are there, as well as what is it that you want to achieve. And so you need to pick and choose and make the solution cost, what is the factor that you're trying to maximize, all that match each other, right? And then we'll conclude with a simple set of takeaways. So what is it that I would like you to remember having heard this lecture, right? So just stepping back a little bit, even when you have questions, you can feel free to stop me, but I believe what I am telling you should be fairly easy to follow. So we will have time at the end, so I can stay back even beyond an hour if needed to discuss anything more. Okay, so as you would know, in the development of the CPU, Intel always played a big role. So we came up with this idea of the central processing unit, where you have a processor that can look at a series of instructions that is sitting there, pick them out, execute, and get something done, right? And the general model that we have been using long way back from the 70s is that you write as some source code, let's say in C, and then so that is whatever code that you have written, and then you run it through a compiler, and the compiler makes sure that it is giving you a binary that is compatible with the type of CPU that you are going to run it on, right? So it could be an output for an Intel x86 CPU, or it could be an AMD CPU or an ARM CPU, whatever it may be. So in general, whatever code that you write, depending upon the compiler you use, you can spit it out for different kind of processing units that may be out there. So once we got this particular design model in place, then there were so many different kinds of CPUs that have come out. I'm sure you can probably list out a lot more than what I can. So it's not just Intel and AMD anymore. And Apple has its own CPUs, and for the telecom world, there are so many different kinds, and even companies like Amazon have started designing their own chips. And so there is like a myriad, there is a wide range of chips that are available, some proprietary for a particular company alone for their own use. For example, if you take the Apple's M1 chip, you can't generally buy it because they design it for their own computers, whereas many others that like Intel's, you can buy it in the open market to design your own systems, right? So that was the original model. So as it evolved, Of course, we were constantly making improvements in the chip building technology, making it faster and faster, adding some special instructions for you to do XYZ, all that. So it was continuing to develop throughout the 80s and 90s. But at some point, we generally started realizing, hey, while this flexibility is extremely good, you can write whatever code you want and then make it work. At times, you may need an external processor that is more specialized to do some particular type of processing, right? So this became popular way back during the Intel 386 kind of time frame. Many of you may not even have born at that time, but we used to have this 387, which is like a math coprocessor that was available to work in conjunction with a 386 kind of device. So what used to happen is if the code that you are running is simply some general purpose CPU stuff, then this blue line indicates that it goes in, comes out, gets processed. But if something is math intensive, then this CPU itself will outsource that part of the process to this external processor, which will do all the math-centric operations and bring the results back, and then it will come out of the CPU, right? So it's like outsourcing part of the work. So this was great, and this is, you can still see there is general purpose computing and maybe some math intensive computing. This was going on, but in the 80s and 90s, the internet started coming up, and so now we get into the part of the actual Ethernet packet header, where you have a source and destination address and that need to get processed and so forth. So you are familiar with this header construct. So when this was happening, initially, the processing itself was done in the general purpose CPU because there was just a little bit of traffic going here and there, and maybe it could handle. But as internet started growing and there was lots and lots of packets that need to be processed, people were quickly noticing that the general purpose CPU is not really built out to do this, or you can do this in a much better, faster, cheaper way if you custom build devices that are meant to do only one thing. Right? So you can. If you're not speaking, if you can mute yourself, it'll be great. We hear some noise on the bridge. So there were a lot of companies that came out saying, let's design silicon engines that are custom built to do just one thing, right? So a good example or an analogy that we can keep thinking about is, since this is like looking up an address and then forwarding it to different location, routing, etc. You can think of it like a post office, right? In the post office, you can have a clerical person who can be trained to sell the stamp in the front, maybe sort the incoming mail, and then actually go deliver it, whatever it is. It's a human being. They can do whatever you want them to. They can be trained to do everything, but they can do it only at some speed, right? And the speed cannot be increased beyond a point. So there were opportunities even in the physical mailing processing world. I was just looking up when I was writing some article. In the 1988, there was a paper mail sorting machine that was designed installed in New Zealand. So apparently it could do 20,000 physical letters, right? It can like sort them out and put it on different bins, 20,000 sorts per hour, right? In each hour, it can sort 20,000 letters. This is still phenomenally faster compared to an individual clerk, or even if there is like 10 people standing there, they may not be able to do 20,000 sorts in 1 hour, right? So this was a phenomenal step up. But just 20 years later, in 2008, there was another machine design that could do like 32,000 sorts per minute. Notice this is 20,000 per hour, but this is 32,000 per minute, right? The idea here is these machines can do a phenomenally good job of doing just one thing, right? So you cannot train this machine to go to the front of the post office to sell stamps, or ask it to go deliver letter mail to different homes or anything like that. Human beings can do all that stuff, but these systems cannot. But when you have this kind of load, when you have this much of work to be done, rather than employing 1,000 postal workers to sort, even then they can't do 32,000 sorts per minute. Employing such a machine becomes much more efficient, right? So that notion is brought into the processing of packets in the computing world also. So including the companies that we were on. So originally, when I joined Lucent, the first device that I worked on was actually in the ATM network world, but subsequently the Gear, LSI, different companies that I was part of, we were designing modules that actually had no CPU capacity at all. You should think of it just like that sorting machine out there. So it'll just have a set of registers that you can go and set to certain values, turn it on. It'll just keep doing the same thing over and over, but it can do it much, much faster, right? And on that notion, at one point, we had this one accelerator, silicon accelerator engine called Modular Packet Processor, MPP. So that can really get into individual packets that are coming in, work at the bit level, right? So we can actually write code that will say, okay, take the new Ethernet packet, skip so many bits, look what's there, and then do something, right? You can write that kind of code. So let me just show you just one quick example of what we are talking about. At this stage, all these kinds of things may be available to you as a ready-made library. You may be just integrating and then running with it. So at some point, just looking at it, how things get done at the lowermost level gives us some clearer insight, right? So the company that we were on actually had this language called FPL, Functional Programming Language. The data that is actually flowing in comes in as hexadecimal characters that are coming in, right? So initially the pointer is sitting here. So we are at like function A that is saying F skip, F meaning forward, skip 16 bits. So when you actually do that, you can see this pointer has moved to this location. I hope you can see the mouse moving, right? So this red triangle is indicating that you moved forward 4 steps, and so you are here. At that point, you want to find out whether it is a IPv4 packet or an IPv6 packet. Depending upon whatever it is, you will, if it is IPv6, you're going to do some function F. If it's IPv4, you're going to do function C and so forth, right? So when you do this, it comes here, and then it figures out, aha, it is 4, and so I need to go and execute this part of the code, right? So it actually like steps through these things, but the point is, it's not going to be able to do a lot more than this. So there is a set of FPL instructions and what it is capable of, all that's available to you, and that's all it can do. But it can do it at a phenomenally faster speed than what the general purpose CPU can do, right? So that's the overall takeaway. Here, the original accelerators that we were working on didn't even have any CPU capacity at all. So it will just have these hardware engines that you can go and program. Some used to be capable of running some small amount of code like what we were showing, that FPL code. So you can actually write some code, put it in, it keeps running that same thing in a loop. Or many others did not even have that kind of capacity. It just had bunch of registers. You just go and write some value, turn on, off, and then let it run, and then it kept running, right? So when this was working really well, then we also added a lot of additional engines of the same kind. So in addition to this modular packet processor that can pull in new Ethernet packet, do address lookup, forward it to port A versus port B, and so forth, we also had like a traffic manager, so it can police the rate of traffic. It can do stream editor, meaning as the packet is just flowing through the system, it can change some bits from one to the other, right? Things like that. So there was like timer manager, and then there is a security processor, DPI, which is deep packet inspection engine. EIOA is actually the input output part of the device that was there. But even to get these things booted with the right firmware loaded, with the registers configured, you always required a CPU. So you can think of it like in the post office example that we were talking about, you may have this huge letter processing machine, but it's not going to come up and then start doing everything on its own. So you still need a person, the operator, who comes in, loads all the mail that came in, powers it on, or maybe sets up the bins right, and then turns it on to let it start processing, right? So you needed some sort of a CPU. So in the 22 years back when we were working on it, we used to have this pure accelerator and then a separate x86 or some small CPU that will just turn the board on, go and configure everything, and then let it run, right? At some point, people started saying, hey, you always need a CPU, so why don't you put a small CPU in your accelerator device itself? Then we thought, okay, yeah, let's do that. So we started putting a small device, and then it became more like, hey, if you have a device, we actually want that CPU to do some more. So can you make it bigger, better, faster? And maybe instead of one core, you put 2 cores and things like that. So it kept growing that way. So at different points in time, we used to have different kinds of CPUs that were in the system. So we had worked with PowerPC CPUs, we worked with ARM CPUs, and there are so many variations now that we are Intel's low power processors are these Atom processors. So our latest ones have Atom processors in there. So irrespective of exactly which processor that you are using, this model became quite successful, and they are still in use. So usually they are referred to as SoC, meaning system on a chip model, meaning anything that you want to build. So for a post office, you may need not only the sorting capability, but you also may need some stamp vending capability, and maybe bringing letters into the post office and taking stuff out of the post office. So think of it like IO. Maybe when there is some interaction needed with the external customer, how do you do that? All those things that are needed, you can put everything together as one post office, right? So to build some such system, we started building chips that are system on a chip, meaning to build this entire system, everything that you need is under one device, right? One chip. So it not only had this modular packet processor to do traffic lookup or deep packet inspection to look for virus or anything like that. It also had EAOA. It had a bunch of processors, so it can also do a lot of processing where flexibility is needed, right? All that thrown into one. And then there were different variations. So for example, if you are designing a system, I mean, a chip that is mainly to run a laptop or a desktop, you probably don't need some of these engines, right? So depending upon what is it that you are trying to do, you may pick and choose what engines to put in and how much to make, how powerful to make these the core CPUs more or less, and so forth. So this model is quite successful. And so there are variations of this called ASIC, application specific integrated circuit, where it's not a full system. You may need an ASIC and then some other CPU and then some other FPGA, this and that, all put together to make a device. But that FPGA, sorry, that ASIC is very custom made, let's say, to run a cell tower, right? So you have like radio traffic coming in, you need to be able to process it and then do some processing and then send it out in the other direction. So those kinds of ASICs are, if you are really working with a particular customer, let's say Reliance, and then they want not just an ASIC, but I want to put all that I want into one big chip that can do processing, packet forwarding, lookup, DPI, this and that, then we go into SoC designs that will take care of that requirement, right? So why do we keep doing it? Because there is still, each one of this gets tailor-made, and so they fit a particular area of processing really, really well. So this ACP stands for Axia Communication Processor that we were doing before. So if you generally look at it, depending upon what bandwidth that you are looking at, less than 5, 10, 20, or more than 40 gig, this slide is still a little old, right? So now you can think everything has become 10 times more, etc. And whether you are trying to do L2, L3 processing or more L3, L7 kind of processing, which OSI layer you are in, depending upon that, there may be some sort of a network processing unit, which means it's not very flexible. It can do L2, L3 only, but it can do that phenomenally fast, right? Or you go to this end where it's a communication processor, meaning you have a lot of CPU capacity, and so you can do whatever you want, but at a much lower speed, right? Or a combination of these. So the ACP that we were working in, it was kind of in this range. So it can't compete with NPU level, but it's much more flexible than a regular simple CPU kind of thing. So depending upon the vendor, the application, the system that you are trying to develop, people would choose which kind of combination model that they want to work on. And companies like Intel work with big tier 1 customers. So if like Reliance really want us to design a particular kind of chip that will have ABC capacity, all that put into one, as long as there is good margin, we would work with such people, such customers to build a chip, right? So these are extremely expensive to build, and it requires a lot of testing capacity, QA, verifying, and so on and so forth. So ideally, we want to design one that can be sold to a lot of different customers. But if there is a customer that is willing to pay a lot of money for one particular combo, because if you design something like that, when you make them in millions, the cost comes down, and then in the end, their overall the operating expense would actually come down, right? So need to pick and choose what is it that you are trying to do. I hope what I'm saying makes sense. And these are just a couple of examples in which these ACP kind of devices keep getting used. What I want you to kind of understand or remember is, in general, the fast path would refer to the data path where there is a lot of traffic coming in. Think of all the Ethernet packets that you are talking about coming in. You need to move forward, look at the IP address, and then send it to some particular port, right? So this is like a production line. You have tons and tons of packets coming in. You just do a lookup forward. So it's like switching, that kind of thing. If it has to happen, it's called fast path processing. So most of the time, just this hardware engines that we are talking about can simply handle them. So you can design paths through the system where this entire fast path processing is handled just by these hardware engines, whereas the CPUs that are sitting here are never touched, right? So you are not loading them up at all. But sometimes you do need to do some pre-processing. So an example would be, let's say you have like MAC address learning, right? Even at your home, if you are connecting a new device to your network, the MAC address gets, first time when it comes in, the router wouldn't know what device is this. In that situation, this black arrow shows that the fast path would say, hey, I don't know what packet this is or where to send this because I don't see this MAC address in the table, port forwarding table at this point, right? When it goes up, then the CPU will have code sitting there saying, okay, unknown new MAC address that came in, or it could be anything like that. So a new IP address, and if it is this IP address, packet should be forwarded to that particular port, right? Things like that. When it's not known, then the CPU is flexible. So think of this like there is a brand new address that came in the post office letter sorting facility. So the clerk has to go in and physically enter saying, hey, this is a new division or a new home that we are adding. And if you see this address, put it in this particular bin, right? So you are programming it like programming that machine like that. So that part the CPU can do. But once that entry is made into that table, then that's it. It goes back to this pink line. So it can just keep forwarding the packet in that right way. And same thing can happen even in post-processing, meaning in some cases, it goes up, something gets processed in the CPU, but after that, maybe you need to do some additional processing related to traffic management, some crypto offload, meaning this device doesn't have IPsec or some crypto processing sort of thing, then it has to go somewhere else, come back, something like that. Or there could even be this blue line where everything takes place in the CPU. So all these things are possible, right? I just had one or two quick examples on this IPv4 forwarding itself. This is using this modular packet processing. So in this case, this EIOA, you don't need to remember any of these abbreviations. I just wanted to give you a sense. So this is, just remember this IO. So this is Ethernet input output adapter. So this is IO, right? So it's traffic coming in. When it is coming in, there is a task created in the queue destined to MPP, meaning, hey, there is a new packet, we need to process this, right? So that happens through the EIOA interface. Then MPP, which is that modular packet processor, will keep picking packets one after another from the queue, right? And then it's going to go back to that function code example that we were looking at. Okay, start here, skip so many characters, look what's there, it's IPv4, v6. Okay, if it's a v4, then you do this processing, I am done, push it out, right? So it reads the next task, performs that 4-tuple classification, sends it to the correct port. It says, it writes the task destined to queue, meaning it can go out, right? The processing is done. Then the EIOA reads the next task and writes it back. So it just that this loop, it keeps doing that. And MPP, as soon as it's finished processing, putting it back, it goes back to picking up the next packet. It keeps going in this loop. And this MPP cannot be rewritten to run a database operation or run a web server or something like that. It's incapable of doing that. So simply keep thinking like the post office example of sorting machine, right? But it can do that at extremely high speed. So here you can see this pipeline that is set up. That is the input output aspect module that's bringing the traffic in. The packet processor looks at it and then it sends it out. That's it, right? So there is no CPU here. So this path can run at an extremely fast speed as needed. This is another example where we actually have IPsec processing. So this is for security processing. So when this is happening, a CPU is actually involved as well. So you have this EIOA, that's input output, coming into packet processing. But now you realize, I need to encrypt or decrypt this packet, right? You're not just doing port switching or port forwarding. As a result, it will end up sending it to CPU where some processing needs to take place. It goes to a security processor, comes back to CPU, all that, then it goes out, right? The idea here is you can either, you should optimize and try to push as much traffic as possible without touching the CPU. But if and when needed, there is a path to send that to the CPU. Maybe at sometimes it's a new packet, you don't know what to do, or maybe at certain cases, some processing needs to get done in the CPU, and so you can do that too, right? So both are possible. Again, in these slides, it's okay if you don't understand each one of these things. What I want you to think through is really understand that in the Ethernet packet header or any other packet that you're looking at, this is all constructed by us, right? Communication engineers like us. So often there will be bits that are allocated that are free for you to reuse, redesign, do whatever you want, depending upon what you are trying to do, or certain areas where things are preset so that whether it is coming from vendor A or vendor B or service provider C, when the packets come in, you know exactly where the IP address is going to be, you know where the destination address is going to be, and what type of packet it is. Those things are clearly defined. And whenever there are bits, there are a lot of bits that are actually given to you for you to do whatever you want. And at that time, as you grow into this field, you will see we will break it down into smaller segments and then figure out what we want to do with it. So we might want to put some sort of a stream ID here, indicate how big this particular packet is, maybe put a sequence number here, and we are fragmenting a large packet into smaller pieces. indicate what fragment it is. This is fragment 7 of out of 28 or something like that, right? You can design these, and you need to assess how many bits do you need for each one of these, and then actually write code that will traverse through this bit by bit, assess what is going on here one by one, and figure out how you want to do it. And when you do this, I'd like you to keep thinking that if you are doing this in the CPU can do whatever you want, but it's going to take a lot of time, right? So it's going to take a lot of cycles. And particularly if you do things like you are going forward and then you are trying to figure out, after I figure out this fragment index, I need to see what is the event size. And so you are going back to read the event size. Those things are really bad, meaning instead of just moving forward, if you go and then come back and then go back, those kinds of things will just kill the capacity of the router, device, etc. So you will come to know a lot of idiosyncrasies like that. So you need to make sure you're always moving forward, never keep going back. And if you need to save this, for example, event size, you put it somewhere, and then by the time you come here, you already know what it is. You are not going back to read it. Or if you are the one designing it this way, and depending upon how your application is going to process, maybe the fragment index should come first and then event size should come next, whatever. You can do things like that, right? So you need to start to develop a sense of, all these bits are given to us where we can design what to put where, wherever it's like optional areas. And then there are several areas where it is already preset. There are standards that are defined. So this area, this particular bit, this field is going to indicate XYZ, right? So you can't change it. So we do these kinds of things all the time for our vendors, and this is particularly common in the telecom sector, where we might have to design our own frames and indicate something in some location and use that to do things much more efficiently. This one just gives an idea of why this notion is important. This is because just normally, if you do everything in software, right, your performance tends to be at this level, right? And whether it is 64-byte packet or 200, 1500-byte, whatever packet it is, you kind of get this kind of low performance. This is using CPU all the time. But as you start doing, let's say, IPsec, you're doing it in look-aside sync model, meaning CPU and the IPsec processors work in sync or async. You can keep increasing the capacity more and more. I want you to pay attention to how this graph looks here. That's because if it is 64-byte packet, if you have same amount of information, right? Think, let's say you have a book and the content of the entire book is written in 64-byte packets, so then you are going to have a lot of packets. And so in this situation, the hardware engine that is dealing with it is actually dealing with a lot of packets. And so the capacity may be low, right? But as the size of the packets become bigger and bigger, you become much more efficient. And so it can actually get the entire book out by processing just a few packets, right? So that's why this curve looks like that. But if you can fully offload that completely, then you really get much better capacity. And then you go all the way to raw crypto, meaning what is the capacity of the device, the IPsec performance itself. That could be like 200 times faster or more than what pure software can do. Right, so this is what is the incentive. This is the reason we want to use hardware acceleration engine in general. So this is an older chart, and this is from our latest Xeon device that is just coming out. So in this case, you can just see the dark blue indicates ABC News, and then light blue Shanghai Times, yellow CNN, and red Times of India sites. What we are trying to do is run this Nginx web server kind of thing, and we are trying to do 100,000 requests per port. So we are trying to do there's so many requests trying to like connect the websites back and forth. If you are trying to do that, the completion time, meaning how quickly is it able to do that. If you're doing it completely on software, you can see, depending upon the sites, it's taking this much time, right? So the lower, the better, if you can finish it much faster. If you use this Intel QAT, which stands for encryption decryption engine capacity, you can see it's much, much lower. And even in these particular cases where the number is like some 150 kind of thing, units of time that it took for completing this 100,000 requests per port, that's actually drastically reduced down to less than 40, right? So this is because we are using this hardware acceleration engine. And here again, it's connections per second. So in this case, you can see it's like a different thing, PKE compression crypto. So you can see fewer connections, meaning we are not measuring the time, but how many connections can you do? So here, higher is better. So you can see if you're doing it purely with software, it keeps coming down. So this is an inverse of this. Since it took this long to finish so many connections, if you just measure it, let's say per second, how many connections you can potentially make, it's only so low. But if you switch to the QAT mode, then it gives you a lot more, right? So this is the advantage, meaning that the performance capacity that you are going to get is going to be lot more when you use the acceleration engine, but you lose some flexibility. You cannot make it do anything else that the CPU can do. That's the downside. And often you're also tying yourself to this particular architecture, particular module, particular programming style to get this advantage, right? And so if you want to move from this system to another system, and in this other system, you don't have this kind of an acceleration engine, you may need to rewrite some of the code to make sure it runs on the general purpose CPU or some other accelerator that may be available there. That's kind of the negative side to this, right? So that's what you should keep up. So companies like Intel, I mean, one thing you should really internalize is we belong to a field that is bringing in phenomenal value to human civilization on the whole, right? You take any other field in the world, agriculture, biotechnology, medicine, whatever it is, you never see the cost of the service coming down so much and reaching so many people all around the world consistently. Our field is the only one that is actually doing it like that. And in order to do that, companies like ours need to really keep looking at all the fields, all the services that computing industry needs to provide, then keep coming up with newer and newer devices that takes care of all these computing needs. So this is just to give an idea of, it's not just CPUs and accelerators alone, but so many different kinds of devices that are put out. So we talked about CPUs, we talked about accelerators, we also talked about FPGA, which is field programmable gate array, which is like a breadboard, right? It's like a generic device into which you can actually pour a particular silicon design in, and then it starts running, functioning like that particular chip, custom designed chip. But of course, that again gives you some flexibility because you can remove that image and then put a different image and get it to run. You can read more about it online, or you already may know about it enough. But because of that flexibility, again, the cost of those devices are a little higher than an SoC or an ASIC device that is custom built just to do one, right? But we do that also. There are areas where that is needed. So if you take just Intel alone, for autonomous driving, we have separate chips. And then for 5G network, we have set of devices. And then cloud computing, IoT, client computing, AI. For every area, the Stratix is that FPGA kind of device, right? And then client computing is more like desktop, laptop computing, so you need low power capacity. Whereas if you really go into data center, cloud computing, analytics, you need extremely high computing capacity. So you have these Xeon devices. So including the latest one that we are working on, are the Xeon devices that do have these kinds of accelerators. So we'll just talk about one accelerator in that domain in the next slide, right? This slide is to tell you that depending upon what solution that you are trying to develop, your requirements will keep changing. So this is just one slide from the 5G talk that I usually give. As you can see, this is to improve mobile edge computing value. So to do this, if you design the network, if you design the systems like the way that we were previously doing, an actual phone may be sitting here, and then it goes to the cell tower, and then it comes through the network to the mobile core all the way back to the data center to get something done. So if your IP address processing, etc., gets done only here, each one of these packets need to come all the way here and then come all the way back for any of the communication to take place, which was okay. That is how originally we started building network. But in 5G, the latency requirements at this edge are much, much, much more stringent, right? So if you take your 4G phone, wherever I go around the world, I keep checking if I just do a ping, right? How long does it take for you to get a reply back? I used to get like 172 millisecond, right? Things like that. Whereas in 5G, the requirement is you should get a response within 5 millisecond, right? So how are you going to change that 172 millisecond it takes for this packet to traverse all the way and come back to 5 millisecond? So if your design remains the same, it cannot work. So we start doing a lot of computing at the edge, meaning we bring a lot of computing to this area alone, this area itself. So if you're just doing a ping, you want it to get processed, come right back. So if the car is moving around, you want to do traffic management. If you need to send all the traffic back all the way here and bring it back, it's too slow. It's not working. It's not good for us. So we want this to happen right here to improve performance, right? So in those kind of situation, we would go for certain kind of chips, certain kind of accelerators to get your end goals accomplished. But of course, that is going to come with its own associated cost, right? Maybe the price will increase, or maybe the devices that you are using are too big for the amount of bandwidth that you are going to need. So you are over provisioning, things like that. So you need to see what's the best possible case. But if it is something else on the other end, if you're just looking up, let's say weather information that has to go all the way and then come back, even if it takes 2 seconds for you to get a performance, I mean, the reply, it's okay, right? So you need to embed that kind of capacity throughout the network to see what is it that need to be processed here now to cut short of latency, and what can be sent all the way back where there is more computing capacity available, and also be sensitive to different kinds of traffic that are coming in. So for example, if you take audio calls, right, they're extremely sensitive to any little latency. So even if it is like 200 millisecond plus minus, you can hear the echo, you can hear the calls getting cut off in your ear. So the call quality goes down. So you need to be able to identify those packets using the bit fields that you have in the packet, and give it highest priority to get that processed as quickly as possible. Whereas if you are, but the bandwidth that is required for each one of the voice call is extremely low, right? So you can process that really well. Whereas if you are just watching a video, you need a slightly bigger bandwidth because video requires more bandwidth. But maybe you just need to download. So there is no latency thing where the bidirectional latency is really important, like where two people are talking on the phone, right? Where so you can push a bunch of video first, and as it is playing, as long as the buffer doesn't go dry totally, as you can keep pushing more video in, you are good, right? So these kinds of differentiation in the quality of service that you need to maintain, the network need to be well aware of that, and that's where all this L3, L7 layer networking comes in, identifying that, prioritizing the right traffic at the right network level so that the quality of service experience that people see at the edge of the network is consistent, good, and it's accorded the right privilege, but without increasing the cost too much, right? So there is always a possibility of over provisioning everything, putting a lot of computing capacity, and everything will be great, but that's going to increase the cost a lot more. And if there is one field in the world again where you have to be extremely cost conscious, it's our field again. If you're designing a new pharmaceutical drug, there is so much of licensing, regulation, this and that, and you can ask for $100,000 for the drug, it will still work, right? But here, if you ask even your own cell phone service, if you are paying 500 rupees per month, and if the service asks you to pay 600 rupees, you will start looking for another service that will provide the same thing for 400 rupees, right? For 100 rupees, people will quickly switch service. So you need to keep the cost very contained as well. So of course, that's what makes the service and system available to everyone. So in the next just 5 minutes, this is the main accelerator that we are working on. So I just wanted to give you a sense of what it is, even though this is not specifically related to layer 3, layer 7 processing. This is called Intel's dynamic load balancer. Literally, this is what my team is working on in these days. This will be part of the next Xeon processor that Intel is pushing out. There'll be a big announcement, etc., in the new year, in the January timeframe. But the device has been shipping. So if you go on the web and search for Sapphire Rapids, right, that's a code name for the particular Xeon device. So this has this accelerator called Dynamic Load Balancer. I'd like to describe this more like, just like what we are talking about the post office case. You can think of this way. If you are landing in an international airport, right? So there is like a huge plane full of people that just landed, let's say 500 people. They all come into the airport, and then there'll be 20 different counters where passport officers are sitting there. Right? And all these 500 passengers that came in need to go through one of those passport processing officers who are going to look at your visa and say, okay, I stamp you, you're all good, you can go into the country, something like that. To do that, a simple model will be these 20 passport officers are sitting there, and then 20 lines are formed, right? But if you follow that model, then suddenly some passport officer 3 goes out for lunch, then the people who are standing there are all stuck. So in most airports, what you would see is all these 500 people standing in one long line, and there's 20 officers sitting in 20 booths. And then there is one person at the head of the line who actually says, okay, you go to counter 17, you go to counter 3, you go to counter 16, right? Things like that. That person who's standing at the top of the line, directing the traffic to make sure that all the 20 passport officers are equally loaded, nobody is idling. That is what DLB does, okay, the dynamic load balancer. So it basically, all the people that are the 500 people that are standing in line, you can think of them as Ethernet packets, right, that need to get processed. And the 20 passport officers, you can think of them as CPU cores that are doing processing, right? And DLB makes sure that all the cores that you have are well loaded. They are all giving their best. No core is actually idling. That's what DLB does to improve the balanced processing capacity of the CPU cores themselves. So when it is all pure CPU based, what used to happen is, like we were saying, there'll be these producers or like the traffic that is coming in, queues will be in memory, and then the consumer or the passport officers, right, picking up the packets to process them. But often this will require like locks to NQ, DQ, put things into the queue. Anytime you used to use lock in software, the performance really goes down because you're locking something, putting something in, removing the lock, then locking something, removing one packet, and then removing the lock. That process really slows things down too much, right? all that is completely taken care of in the hardware in DLB, so things can run much faster. How much faster? This actually gets into different types of queues that it can talk about. Just to give one like simple example, even in the passport office, that person at the head of the line directing traffic need to be aware. Maybe one person is bringing their whole family, so there is maybe a wife, husband, two kids, etc. So they all need to be processed together by one passport officer, right? Whereas the next person is one single person, he or she can go to any of the available free person. So that the person doing the scheduling need to be aware of such requirements. And this slide is talking about all those variations, and DLBs can be made aware of such variations. And maybe there is one person, or like every now and then there is like some special visa category people that need to go to a separate passport processing officer sitting at like cubicle 19 or 20, things like that, right? So similar thing, packet processing need to be unique, and so it needs to go to a specific processor, or a set of packets that need to be processed together that needs to go to one processor. DLB can do all those kinds of variations. So by doing that, instead of the course being more loaded, less loaded, well limited amount of load, all these variation, it goes away and you get the best out of all the course. And because of this, the amount of course needed to process all your packets may actually come down. And each time you can save a core in the computing industry, it's phenomenal, right? So it's a lot of value that you are getting back. You can run more application, or you can dedicate that code to do something else. So this one slide just tells you how the software-based solution compares with this one. We said there are 4 DLBs in one Sapphire Rapids, but I'm taking only one DLB use case here. And so if you're using purely software based scheduling, meaning you do the scheduling with like just one CPU core doing it in software, right? If you do that, the entire capacity of that one core dedicated to do just that scheduling would max out at around like 17 million packets per second. So if you get that CPU to run as fast as possible to do software-based scheduling of balancing all the cores, sending packets to all the available cores, it will max out around, so it can do about 17, 18 million packets can be scheduled per second. It just stays there, right? Whereas if you start using DLB, it can keep scaling up all the way to 100 million packets per second. So if you want the same kind of capacity, you might have to use maybe 6 cores to get this level of scheduling capacity, right? That is 6 core is like 6 human beings. That's much more valuable than one machine that can do that for a lot cheaper, even though this is the only thing it can do, right? This is an external website. The website itself is nothing phenomenal, but this is where my team is publishing all the latest code, etc. So I can send that link to you all, and you can go take a look. Again, why do we need all these complexity, and why do we need to do this? That's because the computing models continue to change, right? So we talked about that edge computing as one case. We can talk about this slide alone for another half an hour. What we are trying to show here is there is an infrastructure, then operating system, libraries, and applications. So this is the traditional computing model. But with so much of virtualization going on, we have this hypervisor model, and then there is a guest OS library, virtual machines running here. This kind of model are containers that contain, right? You can look up these terms online. Each one of this is like a complete computer. So this may have its own address, and packets need to be routed to this particular VM versus this VM. Maybe this VM wants to talk to this VM. All this requires packets flowing back and forth, and routers and switches sitting there routing the traffic back and forth. So day by day in computing centers and systems in the network, things get more and more complex, right? And as they happen, you need to come up with solutions, routing, layer 1, layer 7 models that can still stand up, address all these computing needs. As a result, you need to be flexible in how you are designing your system, taking advantage of all the technologies that are available to you, ranging from simple CPUs to pure accelerators to ASICs to FPGAs to, if you go to the web and you'll see a lot more things like data processing units, intelligence processing units, graphics processing units, right? GPU, DPU, IPU, and Intel started calling it as XPU. So whatever processing unit that you are interested in. So want you to walk away from this talk remembering that the system architecture pendulum swings back and forth, meaning originally we started out with all pure software, but then we started using accelerators. But unlike the post office model, where the clerk that you are employing who can do everything that is needed can do only so much forever, right? So even after 100 years, the human capacity is only that much. Whereas because of Moore's law, because of how this whole industry functions, every few years you get like doubling the capacity of what a CPU can do. As a result, at some time, what you are doing with pure hardware accelerators, architecting a solution that is custom made for that particular architecture, developing that FPL code, that kind of thing, can again be done purely in software because the CPUs have become much faster, right? But again, the computing needs continues to grow. So at some point you figure out, well, I still want to save the code to do more complex stuff. So I want to do more thing in hardware. So there is this constant going back and forth that happens all the time. And that results in pure CPU. We no longer see pure accelerators alone, but accelerator plus CPU together, or ASICs, or DPUs, or GPUs, or IPUs, or FPU combinations. That those are all like a bag of, or the slew of options that you have that you need to pick up to build your solution. So depending upon the location, meaning, is it one computer, one database you are running in one system where you need something to be done as fast as possible? Or are you talking about a 5G network that is spanning the globe where certain things need to happen much faster and certain things can take a little bit more time? So depending upon that implementation, where that function need to happen continues to evolve, right? So you need to think about that also. And as a result, optimizing the solution is always going to be there. So I don't see in our lifetime we'll get to a point where we say, I don't care. You can just do it the simplest way possible. That's because either it might raise your cost too much, or maybe the latency goes up, or maybe the throughput is not where you want it to be, or any other factors and parameters that you can think of. And you want lowest cost, lowest latency, maximum throughput, everything possible. And if that needs to happen, you need to keep optimizing by choosing from the right set of options that you have to put together the right kind of solution. Right? Just wanted to give this one particular link. So you can just look up Packet Pushers. That is a podcast that is available for free online. Since you are all in this field, it might be worthwhile just listening to that podcast. I'm a big podcast fan. If I'm going for a jog, if I'm doing some chore at the back, I keep listening to some podcasts. So rather than having to read a lot of material just online where you just need to sit, you can't do anything else, listening to podcasts often gives you a lot of input in a very easily digestible format. So consider just listening to it. They have multiple podcasts, small one, big one, heavy networking, light networking, and so forth. But if you keep listening to it slowly, you will get the sense of where the industry is going, what is important, and how solutions are being put together. That's my last slide. I hope I haven't going too fast or too slow. It's not too boring. I hope
no, sir, it was perfect.
It was perfect. It was very nice.
Appreciate it.
We got a practical perspective of how things are happening, because we were focusing only on the protocol aspect of
and the algorithmic aspect.
So
package,
how it actually happens in real time.
Yeah, I mean,
it was a...
this field is an ocean, right? So there is so much to talk about. You're all teaching like semester-long courses. So even, I mean, I skipped over that different queue types that we are supporting on the DLB. So just talking to tier 1 customers, we understand 80% of the traffic that goes on the telecom network, it's all atomic queue type, meaning all the flow that belongs to one particular traffic flow need to go to the same processor. And so if you're trying to do that, you can't balance it across different cores, right? So what do you do? So just optimizing that so that we can use multiple cores to do that can become like a 1 hour long lecture.
Yes,
so
because I still remember the famous question in queuing theory, whether to have a single server, multiple queues with single servers each, or to have multiple servers with a common queue. Whether to have two MM1 or MM2 kind of systems.
Yeah.
So that is the typical question that we have in the dynamic load balancing.
Absolutely. Yeah.
And when we talk about these Markovian queues, it obviously becomes like the memoryless properties and all make it simpler.
Yes.
But when it comes to the kind of traffic that you are telling, that all the flows should go through a single processor, that makes the life more complicated.
Yes. Yeah. Because you will have one processor that is one core that's overloaded, and whereas the other cores are sitting idle, right? So, we really do a lot of optimization. I mean, literally, some people who are there on the call have done things like you cut down the amount of code where that locking or that single processor thing need to happen. So you can do a lot of tricks to see, even though that requirements is there, still you can do some tricks to move it around and like try to balance it better. So our teams like really get into that machine instruction level, then moving some statement within this and then releasing the lock here, putting it here, and then you see a bump in the performance, right? So we really operate at that level.
Question, like, can you discuss more something more about those EUV lithography device which was in the utility which you shared? Like,
oh yeah. Actually, I mean that alone can take another hour. But the thing is, Moore's law. I'm sure you've come across it. It was not exactly a law. It's more like a prediction. Our founder Gordon Moore made 50 years back, saying every couple of years the density of gates and transistors can potentially double, right? And we have managed to keep that up in our industry. And to get to that next stage is becoming extraordinarily difficult going forward, because even when I started working in the industry, the latest technology 22 years back when I was out of grad school was 128 nanometer, etc. Right? So that's the distance between the successive lines of transistors gate in the chip. 128 nanometer, right? That is nothing now. So the latest devices that are coming up are in the 5-7 nanometer kind of area. The products that we are shipping now are in the 10 or 7 nanometer kind of range. And now we are trying to push it down to 3 nanometer, 2 nanometer kind of level. And we are running out of nanometer. And so Intel is moving into Armstrong units. In order to do that, I mean, the R&D that is involved is extraordinary, right? So companies like Intel, Samsung, our engineers work with companies like ASML to come up with, okay, what more can I do? How much narrow can I get? What kind of new light that I can use so I can do this lithography even in finer space? And there are not only just like doing it in one way, but there are, for example, FinFET technology. You can look that up online. Things like that, where instead of just making lines, can we make it some sort of a 3D thing, so there is just a little bit more space available for the different layers of transistors to interact. And even though in theory that's good, how do you actually do it in mass scale production to get so many chips made and each one of them working functionally exactly in the same way, right? So it gets like immensely complicated, and this becomes such a capital expense intensive industry. So each one of the new fabs that we set up casually costs like $10 billion. So Intel is setting up a couple in Arizona. So we are spending $20 billion just on setting up two fabs, right? And this is a worldwide competition. So TSMC, which is in Taiwan, is a big competitor to us, and we compete with Samsung, etc. So we all need to invest that kind of money, energy, technology. If you look at that 2-minute video, you can see a speck of tin thrown in, laser pointing at it to make a plasma out of it, to like come up with such a fine grain lithography that we can make the lines a little more thinner, right? And that in the end results in more computing capacity at less power in the next generation device. And beyond that, how we are going to even move it forward, because at some point we are really going to go at like atom level, and there is nothing much we can do, but we can still go maybe 2-3 more iterations before we get in. So 10 years down the line, how we'll keep this going, we don't even know. So there is so much of R&D going into make that still possible. But that's why the chips and I mean, anybody in the world can buy a phone today is because that compaction continues to go, and that reduces the amount of power you need, increases the computing capacity that you need, right? That's what that whole thing is about.
Thank you, sir.
Great. Thanks again. I appreciate you all for the opportunity. We'll meet again at some point.
Thank
Yes,
you,
sir.
sir.
Thank you, sir.
you.
I would like to thank you for giving us a very practical insight into what really goes into the Ethernet processing and all, because we are aware only with the protocol aspects and the architectural aspects, but in real time, how does it process, especially your introduction to the pointer based processing and the dynamic load balancing. All this was a really eye opener for us.
Thank you.
So we could understand how Intel could come up with such efficient processors and the work that goes behind all this. We would like to thank Dr. Vanchinathan sir also for introducing such a wonderful speaker to us.
He in fact joined in between.
Oh, okay.
But yeah.
I didn't notice. So hope to have you in
Yes, sir. So,
physical in person the next semester.
yeah, looking forward,
Yes.
sir. Thank you.
We are
Thank you so much, sir, for
eagerly
your
waiting
valuable
for you.
time.
Yes, thanks a lot, sir. And thanks
Thank
to
you
the
so much.
team from
The
Intel.
student should feel that we belong to a field that brings in so much of value to the people, right? And there is so much more to be done.
Very true.
So I want to make sure you're all excited and feel that in your bones. So thank you.
Yes, sir. Yes, sir. Thank you. Thanks a lot.
Thank you, sir. Thank you, sir. Thank you for your
Thanks
time.
a lot to the Intel
Thank
team
you.
also
Yeah, thank
who
you.
joined with us.
Thank you.
Thank you all.
Bye.